So we're on to Vsepr Part 2. We're actually use these little guys in a minute. So telling you notes, Vsepr Part 2, valence shell electron pair repulsion theory, Part 2. And we're going to look at 3 different molecules. We're going to look at CH4, NH3, ammonia, and water. So I'm going to be kind of all over the page on this one. If I draw the Lewis dot structure for methane, CH4, I'm going to use, oh, never mind. It looks like this. Methane has 1, 2, 3, 4 bonding pairs around it and no lone pairs. So 4 bonding pairs, 0 lone pairs. And according to the table I gave you before class, this is classified as an AB4 molecule. You're not going to use the chart in your book, you're going to use the chart I gave you. An AB4 molecule has the shape of a tetrahedron. So when you look at the geometry, which is on the far left-hand side of the table I gave you, this is a tetrahedron. Tetrahedron or a tetrahedral molecule. Okay, what that means is it has 4 faces. My hand is under one face, there's another face, there's another face, and there's the other face. But it has 4 faces. 1 on the bottom and 1 on each of the 3 sides. 1, 2, 3 sides. It also has a bond angle of 109 degrees, or 109.5. 0.5?
Something like that.
109.5 degrees. That is as far as each of these hydrogens can be from each other if you have 3 dimensions to work with. Now, if you look at NH3, its Lewis dot structure is going to look like this. And it's got a lone pair on top. We're going to count up the lone pairs. A is always the same. You know, I should have written this down before. Okay, let me do this over here real quick. A equals the central atom. Should have given you that first. B is the number of bonds on the central atom. And E is the number of lone pairs on the central atom. Okay, sorry, that was rushed. A is the central atom, B, the number of bonds on the central atom, E, the number of lone pairs on the central atom. It's not the total number of lone pairs in the entire molecule. So for ammonia, A represents N. There are 1, 2, 3 bonds to it, so it's an AB3 molecule so far, and there is 1 lone pair on the nitrogen, meaning this is an AB3E molecule, because we have 3 bond pairs, or 3 bonds, and 1 lone pair. When you look up that shape, you find AB3 in that chart I wrote down, that chart I gave you. You look to the left, you see that this is called trigonal pyramidal. Trigonal pyramidal. So similar to the Cal State Long Beach pyramid, which is a square pyramid, this is a triangular pyramid. It has a triangular base, yet it's pyramidal in shape. So trigonal pyramidal. The lone pairs are up here. The lone pair. You never actually put the lone pairs on a model, but they're here on top. They are going to push these guys closer together than they were in methane. And this angle between H and an H is around 107 degrees. So the difference between these two is this bonding pair didn't take up much space. Oops. The lone pair up here takes up more space, and it's going to push these bonds closer together than they were in this case. Now let's look at water. Okay, I'm going to draw water on an angle because it's easier in this case. That's the Lewis dot structure for water. It has 2 bonds on the central atom, and it has 2 lone pairs on the central atom. Okay, 2 bonds, OH, OH, 2 lone pairs. The lone pairs are going to take up a lot of space. Using the ABE designation, this is an AB2 E2 molecule. And if you look that up, find AB2E2, go from that column over to the left, you will see that this is called a bent molecule. That's it, just bent. All right, that's why water isn't linear. The lone pairs are here. Well, actually, the lone pair is back here and out here in front facing the camera, and they squish down the bonding pairs. They're what's making it be not linear, and this angle in between here is smaller than the previous 2. It is 105 degrees. So as we add lone pairs to the structures, the angle between the central atom and the hydrogens becomes less, and it's due to the repulsion of the lone pairs for each other, or the repulsion of the lone pairs for the bonding pairs. So what you're going to do is take correct Lewis dot structures, give the molecules you have this ABE designation, and from the ABE designation, you are going to determine the geometry of the molecules. Then, since you can't build the molecules with models, you're going to look them up online and then draw that.